Thank you very much, and thank you, OPAG, for giving us the opportunity to present to you this morning. So I'm representing the Neptune-ODYSSEY team, designing a mission concept study for visiting Neptune and Triton, giving equal weight to both Neptune and Triton, as Triton emerges as being a potential ocean world and a sister body to Pluto. So I think the ice giants have been very well studied in the past, and we had members of all of the previous ice study teams and their leadership participating in our study. I was particularly ably supported by Kirby Runyon, who is our project scientist, and very much my right-hand man on the project, and Brenda Clyde, who's the lead engineer of our APL engineering team. Next slide, please. So Voyager was the first and only mission so far to visit Neptune. Flew by in 1989, so 31 years ago. Discovered amazing storms in Neptune's atmosphere, unique geology on its large moon Triton, and the tilted offset magnetosphere and ring arcs. So we organized ourselves into 5 working groups, and you'll have seen presentations on this at the LPSC. Next slide, please. Thanks, Scott. Yeah, so we did give this, there's a link there to a YouTube recording of the LPSC presentation, which of course was sadly virtual, but that made it easier perhaps to produce these kind of recordings. So please do go and have a look at that to have a more comprehensive sense of the background science for this mission. I'm going to skip through. I've kind of put together one slide overview for each of the working groups, but obviously there was a lot more work that went into that. But I really want to make sure that I can describe the mission to you in proper detail, because we didn't do that quite so comprehensively at the time. So we deliberately planned for a multi-generational mission, which is a very interesting element of our study. I've been fortunate to work with Janet Battisi while she was observing the Cassini mission, and now in our development of Europa Clipper. And I'm very much supportive of having those elements of sociology and their expertise, and any other expertise that we can draw on from other disciplines while we develop our missions, and that's been particularly rewarding. We have a white paper still in preparation for the final round of white papers for the Decadal survey, focusing on those led by David Ranecki, who's a colleague of Janet Battisi's. We're unabashedly flagship, so I've worked very proudly on the Cassini mission, and this has a lot in common with the Cassini mission. It's a very similar design of spacecraft. It has a probe, in this case an atmospheric probe, to go into the planet Neptune itself. And as I mentioned, we arranged ourselves into 5 working groups: Aurora, Magnetosphere, Triton, satellites and rings, Neptune, and exoplanets. For Triton, in the proposal, we had quite a lot of pre-proposal presentations as well. And we decided before we proposed that we weren't going to include a Triton landed element. And it was a very difficult decision to make. And I was particularly disappointed that we hadn't put that in. But in terms of risk and cost at that point, we thought it was, it was the appropriate thing to do. And actually our only minor weakness when we got our review back was that we hadn't included a Triton landed element. So we then took that as being our instruction to actually do a bit more investigation of a Triton lander. And so we came up with, and Linnea Quick was leading the Triton science from the landed element, and Alan Stern leading from the orbiter. We came up with the idea of an L-cross style ballistic impactor. So no science instruments on the surface, but an impactor which would produce a plume, which then the orbiter would fly through. So we gave that, we pulled on the thread as much as we could, and in the end, actually the risk to the spacecraft of flying so close to Triton was deemed unacceptable, even though and we presented it to Planetary Protection too, who also were favourably minded to that kind of a lander. And also we were worried that a plume, a body like Triton, holds its secrets closer than Enceladus does, because it's such a much larger moon. So the idea of having the plumes as easily accessible to an orbiting spacecraft as you have it at Enceladus is unlikely. So again, we didn't have a landed element, but we did have a science traceability matrix, which we've included as an appendix in our final report. All right, and we had, oh, and also I think I mentioned exoplanets. We had quite a large working group effort to exploring what measurements astrophysicists would like to see at ice giants to understand them in the context of our solar of exoplanets that are being discovered, but also using the cruise phase and some of the time at Neptune too to look back at our solar system in the context of exoplanets. And I think that's got enormous potential for a mission with such a long cruise phase. And imagine making an orrery of the kind of a movie of the inner moons. Right, next slide, please. So in the last planetary decadal, the top and only priority for a new flagship mission was the Uranus orbiter and probe. That was after the Mars 2020, which I very much enjoyed the launch of this year, and Europa Clipper, which I'm also proudly a member of the team of, which will hopefully launch in the next few years. Next slide. The priority changed from Uranus, and those of you who are familiar with my work will know that I've long supported a Uranus flagship mission. I'm not necessarily here to advocate for Neptune over Uranus, but I did rather, it became clear in my mind that allowing for the New Horizons quality science every month of a flyby of Triton is just incredibly valuable, and the amount of interest that the public had in the exploration of Pluto, I think that this is an important part of the buffet of options that are available to us as we decide how to visit the only class of planet in our solar system that hasn't yet had a dedicated orbital mission. Next slide, please. So the question of, is Triton an ocean world? I'm going to skip over these quickly in the interest of time. So as you hopefully are aware, that Triton's sparsely cratered surface showed evidence for geologically recent resurfacing, and an atmosphere response to seasons. Was extreme southern spring at the time of the Voyager flyby. So we're anxious to get back while the southern hemisphere is still in daylight. So our mission will arrive at Neptune, depending on whether we are able to get ourselves organized to do a Jupiter gravity assist or not. It'll be 2042 or 2046, which is while the southern hemisphere will still be illuminated. Next slide, please. This is showing you the family of Kuiper Belt dwarf planets that we know so far, and just to illustrate, there are a huge diversity. They're as diverse as the terrestrial planets, and I'll just reiterate, the idea of getting into orbit around one of these is very ambitious, and you'll hear more about our plans to achieve that in the next presentation. But for now, we have, albeit geologically reactivated and modified from a tumultuous entry into the Neptune system, but we do have a captured Kuiper Belt dwarf planet that's slightly larger than the moon Pluto, that a mission to Neptune could make unprecedented advances in understanding our neighborhood of extremely far from the sun dwarf planets. Next slide, please. So I love this image. Neptune's moons were normal until Triton came crashing in. And I often say, and it's a little bit glib, but it's got some truth to it, that Uranus is a disrupted ice giant. It's had some tumultuous past that's tipped it on its side, but it has a pristine ring system. Whereas Neptune, arguably a more pristine ice giant, has a very disrupted ring system. But as Tracy Becker and Matt Hedman ably illustrate, and again, I urge you to go and have a look at the LPSC talk, the rings and the moons that are left are very fascinating. And next slide, we've got the bullets. Yeah, so the ring arcs changing on the timescales of years. We've even seen them disappear. How the rings confined and how do they evolve? So a disrupted ring system, which we can somehow, a little bit put an age on, is an incredibly powerful thing to be studying, especially in the wake of studying the ring system at Saturn. So a lot to be done there, and a very exciting area of research, irrespective of the fact that they've been so disrupted by Triton's arrival. In fact, somewhat because of it. Next slide, please. Also, Neptune's magnetosphere. Like Uranus, it's a very peculiar tilted magnetosphere, and if this was a movie, you'd be seeing that dipole moving across your eyesight from left to right and up and down. And that's particularly fascinating for me. I love looking at planetary aurora and the idea of where the footprint of Triton might be on the planet of Neptune, and also developing our models to look at these highly offset and complicated magnetic fields. And the radiation belts, which seem to be organized by Triton's outer orbit too, will be an important area of study. Next slide, please. The Neptune, the planet itself, is Neptune as an archetype. It's one of the most commonly found exoplanet types, especially the sub-Neptune super-Earth types. It's also, the bottom right, talking again about the magnetic field. I'm cut my teeth working on Saturn, and it's made life a lot easier for us in a lot of respects because it has a very aligned dipole. It's one of the major questions of remaining at Saturn is why. but it certainly made a lot of our analysis more straightforward. I also work on the Juno mission at Jupiter, which is mapping Jupiter's magnetic field and from very close quarters. So that's enabling us to develop models to handle these more complicated models and understand how they map at high latitudes, both of which are vital before we get to Uranus and Neptune. And I hope my modeling colleagues, and certainly from a data analysis point of view, I would say we are ready. We can do this now. We have very sophisticated modeling teams. We have this paper in particular with Krista Sutherland and Sabine Stanley is a lovely example of working from the inside to understand the origin of the magnetic field that will be measured from our distant magnetometer and learning how to make those links. And it boggles the mind, but I think that boggling the mind is kind of what we're about at the cutting edge of science. And I do believe that we are now ready to really do proper analysis of these very complicated magnetic environments. Next slide, please. So hopefully I've left enough time to go through the mission. So our mission, we named it Neptune-ODYSSEY. We enjoyed coming up with the name and our branding, and this is our fact sheet, which I'm sorry is a little bit small for you to see on here. We were guided by 5 main mission goals. We came in with a cost of 3.4 billion. The science instruments I'll go through again in a minute, but and actually I'll talk about the trajectory as well in a minute, but just to note, the 16 years is direct to Neptune. We chose this because using a Jupiter gravity assist, we had to be ready to launch by 2031. And I was concerned and picturing myself on the Decadal survey, or picturing people like me, that if I had a mission in front of me that was as big and important as this one, that said I had to be ready to launch by 2031, it would make me very nervous to say, this is the mission we should select. So I was very, I took it very seriously to provide a mission concept which will allow for launches every single year, albeit at the expense of having to assume longer lifetimes of the instruments and the RTGs, and of course an extra 4 years before we really get to do the great science at Neptune, which is one of the reasons we talk a lot about what we can do during the cruise phase as part of our study. Next slide, please. So this is the concept study team. It's a very large team, so I'll just put it up quickly so to acknowledge all of their excellent contributions, and so at least the photons from their names can hit your eyes. Next slide, please. So we started, this is developing the STM. We started with the mission goals, as you see on this table, and along the top are the instruments, with the atmospheric probe second to last, and then radiogravity science at the end. The questions are, how do the interiors and atmospheres of ice giants, exoplanets form and evolve? What causes Neptune's strange magnetic field, and how do its magnetosphere and aurora work? Is Triton an ocean world? What causes its plumes? What is the nature of its atmosphere? How can Triton's geology, geophysics, and composition expand our knowledge of dwarf planets like Pluto? And what are the origins and connections between Neptune's rings, arcs, surface weathering, and small moons? So as you can see, it's an enormously diverse mission, as I believe befits a flagship. It really does encompass everything that OPAG has under its remit, and certainly most of what the Planetary Science Division is tasked to explore. Next slide, please. So we worked very hard to produce, I'm sorry this came out a bit blurred on the PDF. We worked very hard to produce a science traceability matrix that would fit on 3 pages so that we could have it in the main report. I'm sure anyone who's been involved with studies like this must have gone through similar headaches, and I was very glad that we had significant expertise on the team to help us develop this. So our science traceability matrix in the report reads as it should from left to right, and then we've added those coloured boxes to show which of our science objectives map to which of our main mission goals. And then we have the instruments identified in the 3rd column, which then, next slide, led us to identify this as being the ideal payload. Again, I do apologise, it's a bit blurred. But we focused on making sure all of our instruments had a heritage instrument that they could map to in order to provide what we call a shovel-ready concept, so that if NASA choose to stand up this mission tomorrow, all of the needed elements already exist apart from the RTGs, well, apart from the plutonium for the RTGs, in fact. So I'll encourage you to go and have a look at the final report to see if how your favourite instrument has landed there. I did start with allowing us to have somewhat of a Christmas tree of instruments, and actually in the cost cap, with all of the advances that we've made in recent years on miniaturization and things like that, we got almost every instrument that we wanted on the payload. There's a few small augmentations. I'll highlight one in particular, which is there's a gap in the UV range, which I gather is common to many instruments, to many missions, which I'm hoping that the small amount of instrument development could address. But otherwise, it's a really comprehensive mission package. I'd be thrilled to see this get into orbit at Neptune. Next slide, please. So here's the configuration of the spacecraft. The 3 RTGs are on the bottom. They're the green large things sticking out the side, and we've got 4 thrusters around the bottom too to allow us to do maneuvering in orbit. The probe is on the side of the spacecraft, and a large 4-meter high gain antenna on the top to help to save power. So very familiar design, very similar to the Cassini spacecraft. Next slide, please. Thanks, Scott. And then we return to the science closure from our proposal document to produce a science section in the final report that demonstrates how the defined payload meets the mission goals. So in order to provide closure, so that we start with our mission goals, we developed our SDM, we identified the instrument payload that would do that, and then we take our instrument payload and we go back to what were our original proposal science goals, and then we write the section in our final report drawing on those initial proposal goals. And I think that was a very satisfying way to make sure that our final mission does actually close in the science traceability. And we have no figures in that section of our report due to space constraints. So it's a little bit dry of a read, but there's lots and lots of links, and we've been careful to put active links that will direct the reviewers directly to websites and existing documents to look quickly for any extra information, as well as having quite a comprehensive set of additional information in the appendices. Next slide, please. The tricky bit, so just to make sure we're addressing it head on, is the need for plutonium. So this is a slide we modified from June Zagraszczyk's talk to OPAG last year. So you see the orange bar are what the future holds if we stay at the current production of plutonium, which is I think 1.5 kilograms a year, and we select a Trident nuclear mission for the Discovery next phase, then we'd need to increase the nation's plutonium production. That's the orange bar. We go below the 0 for selecting a 3 RTG mission such as Odyssey in 2030. If we decided against a nuclear discovery mission, then we would have just enough to do a nuclear mission to Neptune. Or we can increase, I've seen, and I've been looking at the website, that there's the potential for having slightly increased plutonium production, but I don't know how realistic it is. But if we could increase to something like 3 kilograms a year, then we would have plenty for these missions. So it's very important for NASA to continue to advocate for the production of these nuclear fuels. Next slide, please.
Abby, 3 more minutes.
Thank you, I know. All right, so our launch vehicle decision path, we decided on the SLS Block 2 with a kick stage to allow chemical direct to Neptune. This allows you a launch every year. And I really want to stress this was made a very, very difficult decision. And I feel like it was important to make sure we show how we can have annual launches. But you also, if we get our act together to launch by 2031, we can drop the kick stage, go straight to Jupiter with exactly the same payload, and use the Jupiter flyby. So it's a really easy transition. It's not the detailed one that's in the report. And really the whole mission, it's like an ice cream cone. The mission is the ice cream that sits on top of the cone. Redoing the cone to have this launched by 2031, anyone who's been following along with Clipper will know, is actually relatively trivial. So the mission can easily pivot to including the Jupiter gravity system. I dearly hope that it does. Next slide, please. So this is an infographic showing how we achieve those launch trajectories. The dots are the direct to Neptune, so you can see launch here along the x-axis, and we've chosen, next slide please. We've chosen as our point design the worst case scenario just by a little, which is to launch in 2033 direct to Neptune with a 16-year cruise phase with the dry mass to Neptune, so mass to Neptune orbit on the y-axis of about 3,500 kilograms, which is a lot. And you can get just the same amount of mass if you launch, for example, one of those crosses in 2031. If you launch there, you can get exactly the same amount of mass to orbit, but you get there 4 years sooner. Next slide, please. And I'll skip these in the interest of time. Do look at the report where we detail this. Next slide, please. Next slide, please. So it's showing you that we've got our tour satisfies the Triton local coverage. There's Triton local time at the top and Triton close approach distance at the bottom. And the yellow triangles are the closest approach. And so you can see we fill in all of that dark area of the Triton surface. It's going to be a really fantastic tour. It's a 4-year nominal tour. Next slide, please. I'll move on, sorry for the time. Next slide, please. So we really focus on cross-divisional opportunities, and I'd love to see the cruise phase separated into maybe different disciplines are doing different part of the cruise. We could have some instruments looking at impacts on the spacecraft. Perhaps we could have an EPO camera looking at a surface of metal, seeing how it's getting eroded. We can have exoplanets observations of the solar system. And I'm hoping we did document every close enough to make images encounter with an asteroid or a centaur. And I'm hoping with a few tweaks, a future team could modify that to actually enable a centaur flyby. Next slide, please. So get involved, email me. The link to the Neptune's track list will be on the PowerPoints that you can download from the Neptune, from the OPAG website. And next slide, please. And thank you all to my team, and thank you for everyone for listening. And this is the Neptune-Triton mission, which really is a flagship for everyone. Thank you.